Hey guys, welcome to recitation 15.3. So today in this recitation, I will solve a bunch of problems involving definite integrals. Well, the problems will be more or less computational, but there will not be like super standard computational integrals. In fact, I will show you, I'll do more examples involving this very famous Feynman trick when you can insert a parameter inside the integral. All right, so let's get started. First, I'd like to start with the Putnam problem, which was quite, I want to say very old. I would say quite recent, if you ask me. So it's a Putnam 2016 problem. So, let me just state definite integrals. And of course, I will talk about improper integrals as well. Some of them will be improper integrals. All right, so that will be what this recitation will be all about. So first, let me start with this Putnam problem. So the first problem that I want to solve is this Putnam A3 in 2016. And well, I happened to be at Pitt at that time when these guys took it, when my students took it. And the problem has the following statement. So suppose that f is a function from R and a real value, basically from R to R, such that it satisfies the following function equation. So f of x plus f of 1 minus 1 over x is arctangent of x. So basically arctangent or the inverse tangent function are the same thing. So for all x in a real numbers except 0, and we're asked to find the integral of the function from 0 to 1. All right, so that's the problem. Well, I would say it's a pretty standard problem, but you have to be you have to deal with it with some extra care. For example, well, if you look at this, first we need to analyze the functional equation a little bit. So you see you have a bunch of transformations there. So you take x, then you take 1 minus 1 over x. So maybe maybe this will be cyclic at some point. So maybe if you replace x with 1 minus 1 over x, and then you replace again by 1 over 1 minus x, then maybe you'll go back to x. So that's the main trick, I would say, of the problem. In fact, the first and the main trick of this problem. And after that, the problem will become purely computational. So that's the first observation that we need to do. So first, observe that if we replace x by 1 minus 1 over x, so by x minus 1 over x, and by 1 over 1 minus x. So we see this will be, just like I said, cyclic. So basically we obtain, and we'll obtain these two functional equations. But let me write the first one. So the first one, let me write it again. So let me denote this by 1. So the first one is f of x plus, let me just copy it, write it down here. Okay, then the second one, I said I replace x by x minus 1, everything over x. So this would be f of x minus 1 over x plus f of 1 over 1 minus 1, everything over 1 minus x is nothing else than the arctangent of x minus 1 over x. Okay, so that's the second relation. And now we said we will replace by 1 over 1 minus x. So this will give us a third functional equation. And in this case, we should be lucky because if you replace it there, right, if you see x by 1 minus x, you will get back to x. So basically, you will have that f of 1 over 1 minus x plus f of x is nothing else than just the arctangent of 1 over 1 minus x. Okay, great. So we went back to f of x. Well, if we look at these three functional equations, right, if you just look at them, our goal is to get this guy here, f of x. So we have it here. So maybe we should not subtract 1 and 3. That would be not productive for our goal. So maybe we should add them up. But like I said, we don't want any extra f's there of different arguments. So we want to keep as much as we can in f of x. So maybe we should just add 1 and 3 and subtract 2. So once we do this, we're going to get the following. So let's see. So we get that 2f of x is 2f of x plus is so it's 2, no, it's arctangent of x plus arctangent of 1 over 1 minus x plus arctangent of x minus 1 over everything over x. All right, that's beautiful. And now you see we have a bunch of arctangent here, but maybe we can reduce it a bit further. Maybe we can do something. So second, we need to observe the following. We employed the following identity. There's a very well-known identity, which basically says, okay, let me write it with color. It basically says that the arctangent of t plus arctangent of 1 over t. So this would be pi over 2 if t is positive, and negative pi over 2 if t is negative. All right. So we have in plan to use this identity. Okay, great. So we want to use this. And now this means that, so this implies that 2 f of x plus 2 times f of x plus f of 1 minus x. This guy is nothing else than, well, if we put everything together here, so let's do it in this way. So this will be arctan of x plus arctan of 1 over x. Okay, great. Plus, in fact, let me move this a bit so I have enough, I have more room. Okay, great. Plus, arctan of 1 minus x plus arctan of 1 over 1 minus x, because I have it here. Okay. And now I subtract arctan of x minus 1 over x plus arctan of x over x minus 1. Okay, everything fits perfectly into the picture. So these guys, according to our identity, is nothing else than pi over 2 plus pi over 2. The last one is negative, so plus pi over 2, which will give us, this guy is 3 pi over 2. Great. Okay. Now, finally, it's a very easy remark now that 4 times the integral of f is nothing else than, we can, without change, with the change of variables, it doesn't matter how, well, we'll change the bounds, but this will be nothing else than just the twice this integral, the integral of f of x plus f of 1 minus x dx. And of course, now we can just basically integrate. So this is 3 pi over 2, right? So this means that that the integral from 0 to 1 is nothing else than just 3 pi over 8, and that's it. So that's the final answer. So pretty standard problem. Well, like I said, you just need to be extra careful with 2 things. So this was the first problem. So now the second problem that I have in mind again, this was a Putnam problem a long time ago. I think it was a Putnam P5 back in 1985. Okay, and this has the following statement. Again, we need to evaluate an improper integral. So evaluate the integral. We call this the integral from 0 to infinity of t to the negative 1/2 times, ouch, sorry about that, times e to the negative 1985 times t plus t to the negative 1 dt. I think that's the answer. That's the integral. And of course, we may assume that the integral from 0 to infinity, the Gaussian integral, right, the very famous one, the integral from 0 to infinity of e to the negative x squared dx is square root of pi. All right, we're going to talk about that a little bit because we can also prove it. Usually it's this Gaussian integral, it's usually proved in it has become like a standard problem in calculus 3, where you can prove it using polar coordinates, as I will actually show you when we talk about multivariable calculus. But also there are other solutions, and I will show you. We will prove this one here using Feynman string, as you will see. In fact, I even described it a little bit in the lecture. All right, so like I said, let's insert here instead of this number 1985, which seems to be pretty random, we can just put there a parameter, a positive constant. So it's so for a positive constant a, consider the integral I of a, and this integral is the integral from 0 to infinity of t to the negative 1/2 e to the negative a times t plus t to the negative 1 dt. So if we look at this integral, before we even go further and to see whether this has a value and we can actually define its value, that's exactly what we need to do. We need to make sure that this integral converges. So the first question we need to address, does this integral converge? That is the first question we need to take care of. Well, the thing is that if you look at this, the integrand, right, is bounded by t to the negative 1/2. So, well, the short answer is yes, because this function inside, right, let's call this f of t. So f of t is bounded by t to the negative 1/2 for on the interval 0, 1, right? And on 1 infinity and by e to the negative at on the interval 1 infinity. All right, that's great. So definitely the integral converges. So now what we're going to do, I'm just going to write it. What does this integral mean from 0 to infinity? So we write I of a, which is, let me write it in this way. This will be the limit as b approaches infinity of the following. The integral from 1 over b to 1. So I'm going to split this integral a bit, of t to the negative 1/2 e to the negative t plus t to the negative 1 dt plus the integral from 1 to b of t to the negative 1/2 e to the negative a t plus t negative 1 dt. All right, so I'm going to write it in this form. And now what we're going to do is I'm going to tweak it a little bit. So I'm going to substitute t, 1 over t for t. So substituting 1 over t for t, right? In the first integral, let's call this I1. And let's call this I2. In I1, we have, I'm just going to write it. So we have that I of a, this is nothing else than the limit as b approaches infinity of, now let's see, so this would be the integral from 1 to b. Yes, right, these two will swap. So basically this will be an 1 over t to t. So I'll have, and now once I add these two up, so right, I add I1 plus I2. Keep in mind that we have to add them. So basically I'll have here, so one of them will stay the same. So t to the 1/2. All right, so and the second one will be 1 over t, so dt. Okay, so t to the negative 3/2 plus t to the negative 1/2 e to the negative a times t plus t to the power negative 1 dt. Okay, I hope I didn't do any mistakes in computations, but yes, that should be it. All right. So now there's one more thing we need to do, and now maybe okay, so now use the substitution. Now we should be careful here. Let's use this U substitution. U is a to the 1/2 times t to the 1/2 minus t to the negative 1/2. And then finally, this gives and this gives us. Anyway, I'm just gonna write it directly. I think I've done the computation somewhere here. So this gives us something like, let's see. So I of A is, so U is t to the, so have a factor that will be 2a to the negative 1/2, the limit as b approaches infinity of 0 to, yes, a to the 1/2 times b to the 1/2 minus b to the negative 1/2 e to the power negative u minus 2a, I think, du. Anyway, I think I've done this computation from the top of my head, and I don't think that should be, that's okay. So yeah, I think, yeah, that's correct, yeah, okay. All right, so from here, I think it's pretty clear what's going on, because, okay, we basically have our Gaussian integral, right? So this is nothing else than just 2 to the 2a to the negative 1/2 times e to the negative 2a times the integral from 0 to infinity of e to the negative u squared du. But this guy, we do recognize this, so this would be nothing else than just the square root of pi over a times e to the negative 2a. So that's the final answer. But remember, we're not done yet. We just have to reply for a equals 1985. We have that I of 1985. This guy is, we're just going to replace a by n, so it will be square root of pi over 1985 times e to the negative 2 times 1985 negative 3,970, and that's the final answer. Anyway, it was a bit tricky, but it wasn't hard either. So it was a Putnam B5 back in the days. All right, so now I'm going to make an observation about this. So the thing is that, so first remark, I want to point out a bunch of remarks. So remark 1. As you can see, we use this integral, this one here, the Gaussian integral, and we would like to give a brief account to this integral. So one can prove that this integral, let's call this j, the integral from 0 to infinity of e to the negative x squared dx is square root of pi. By inserting a parameter inside the integral. So in other words, what we call the Feynman trick. All right, so we're going to do this, and then we're going to differentiate inside the integral. So the way we're going to do this is the following way. It's a very tricky way. So for let's say for t, for a real number t, we consider the following integral: f of t and to be the integral from 0 to infinity of e to the negative t squared times 1 plus x squared, everything over 1 plus x squared dx. Okay, so we're going to consider this, and clearly, if we look at t equals 0, right? So if we look at f of 0, so we'll get that this is nothing else, just the integral from 0 to infinity of 1 over 1 plus the x squared dx, which is pi over 2, right? Is the arctangent from 0 to infinity, which is pi over 2. And moreover, f at infinity is 0. So now what we're going to do is going to differentiate under the integral sign. So differentiating under the integral sign, we have, so let's see, f prime of t, this will be nothing else. So this is the integral. Keep in mind, everything is, we differentiate with respect to t. So this would be 2t times e to the negative 2t times 1 plus x squared, which will go with this. So times e to the negative t squared times 1 plus x squared dx, which is negative 2t times e to the negative t squared times the integral from 0 to infinity. What am I doing here? Yes, the integral from 0 to infinity of e to the negative tx squared. Okay, now I'm going to do the substitution. So we perform the following substitution. So we will perform the substitution. So the substitution we will do at this point is y equals tx. And of course, dy will be t dx. So f prime of t, we can write this even further, f prime of t as negative 2e to the negative t squared times the integral from 0 to infinity of e to the negative y squared dy, which is nothing else than negative 2e to the negative t squared times this integral j. That's great. As you can see, we have it here. Right, this is our j. That's beautiful. But on the other hand, we can do something else too. For, let's say, b, right, positive real b, we integrate both sides from 0 to b, and using the fundamental theorem of calculus, we have, we're going to have the following. So you have the integral from 0 to b of f prime of t dt is negative 2j times the integral from 0 to b of e to the negative t squared dt. But this guy here, by the fundamental theorem of calculus, is nothing else than f of b minus f of 0. So basically now at this point, by passing to the limit, so as b approaches infinity, we obtain that. So at this point, we obtain that. So in the last equation, we pass to the limit as b approaches infinity. We know what happens at infinity. You know what happens at 0. So basically, we have that 0 minus pi over 2 is negative 2j squared. Or this is equivalent, if you want, with j squared equals pi over 4. Or this will give us j equals square root of pi over 2. That's exactly what we wanted. There you go. So that's one way to prove. It's a little bit more fancy, but it's not the easiest way. I think there is something in a paper on the internet by Keith Conrad where you can find like 10 or 13 solutions for this, for the Gaussian integral, the most elementary Gaussian integral. So that's the first remark I wanted to point out. But now I want to go back to my initial problem. So the Putnam problem. In fact, it has a deeper significance than it seems at first glance. So let me point out remark 2, because this is more embedded into something, into a very a particular value of a special function. So what we call the modified Bessel function or sometimes it's called of second kind. So there are Bessel functions of first kind, Bessel functions of second kind. Sometimes it's called Macdonald's function, has the following integral representation. So this is a standard exercise in any special functions course. So it has the following integral representation. So a mu of z is the integral from 0 to infinity of e to the negative z cos t cos mu t. And this happens for all these numbers, or this complex number z, whose real part of is greater than 0. So when I take nu to be 1/2 and the substitution u equals e to the t. So this substitution will give us exactly that I of a. So the integral that we found is nothing else than just 2 times k 1/2 of 2a for all a, for all positive a's. So in other words, we have that k 1/2 of z is pi over square root of pi over 2z times e to the negative z, and this happens for z positive. So we have this formula. This is a very nice exercise. You can see this is how deep this Putnam problem is. All right, so these are the remarks. It's a very nice problem, though. Now I would like to do another problem. So problem number 3, which is again a Putnam problem. And we would like to use the same trick. So we would like to use the same trick. So the problem was, I think it was a Putnam A3, 1982. In fact, you can do this in many ways. In fact, we will discuss this problem when we'll do multivariable calculus. So basically, the problem has a very simple statement: compute the integral so the integral from 0 to infinity of arctan of pi x minus arctan of x, everything over x dx. So There are a bunch of ways to do this problem, but I'll prefer to use again the Feynman trick. So in other words, I will insert a parameter inside the integral. So as you can see, I have that pi over there. So maybe I should just insert any positive real. And now we'll do the same thing. So I'll differentiate under the integral sign and so on. Well, in fact, this integral is not, it's just a special case over much larger classes of integrals, which are called Frullani's integrals, and they're very, very important in engineering. All right, but we will make that, we'll point out that remark. So again, consider the integral. So I of A, so this is the integral from 0 to infinity of arctangent of AX, that's arctangent of X, everything over X dx. And for A positive, okay, so I will differentiate. Okay, but first, before we go into that, first, let me point out, it is clear that for A equals 1, I of 1 is basically 0. And we want to evaluate right? So we want to evaluate I of pi. So what happens when A equals pi? All right, great. So taking the derivative with respect to A under the integral sign, what this will give us. So by taking the derivative, this will give us that I prime of A is nothing else than just the integral from 0 to infinity of 1 over x times arc tan of ax prime dx is nothing else than the integral from 0 to infinity of 1 over x times x over, so we take with respect to y, so x over 1 plus a squared times x squared dAx, which is, we look at this would give us the integral from 0 to infinity of 1 over 1 plus a squared times x squared dx. And of course, this is a very well-known integral, is nothing other than just 1 over a times the arctangent of ax from 0 to infinity. And this is 1 over a times pi over 2. All right, great. Wow, that's pretty, it's much simpler than we thought. So now, basically, we just integrate back. So integrating back, we have I of a is the integral of I prime of a dA, so which is the integral of 1 over a times pi over 2 dA. And now we're gonna just gonna do a bunch of computations. So this would be pi over 2 times natural log of A plus C. But now, since we know that since I of 1 is 0, then this will imply, I'll just plug in, this will imply that C is 0. So I of A is nothing else than just pi over 2 times log of A. Wow, that's great. And now it's pretty clear what's going on. So I of pi is pi over 2 times log of pi over 2 times log of pi. And that's the final answer. As you can see, the Feynman trick just solved this problem immediately. Now let me point out a remark. Like I said at the beginning of the problem, this goes back to a much larger class of integrals. So this is a particular case of what we call Rulani's integrals. In fact, I'm not going to prove it. Maybe I'll leave it to you. You can use Feynman's trick for this one as well. Just write it in this way. So Rulani's integrals are in I of AB. So these are for a function which is nice enough so that we can compute this. So it's nice enough so that this integral will converge. So we will have this formula. So times log of natural log of A over B. All right. So this is the Rulani's integral. This is so as you can see, in our case, f of x is nothing other than the arctangent of and of course, A is, let's say, greater than B, greater than 0. This is so the proof goes the same. We just have to do a bunch of some change of variables, but I will leave it to you to do it as an exercise. So you can take the idea from this particular case and you can prove the general case. And in fact, at some point, once you perform the differentiation under the integral sign, you will get a some or ODE. So you have to solve that ODE, and then this will, after that, you'll get this formula. Okay, so this was this problem. Now I would like to solve one more problem. Now probably I'm going to stop. It's very similar to the one given at the Putnam, and which I solved in one of my lectures. So this problem that I have in mind is the following. So it's just a slight modification of the Putnam problem. So problem 4. So this was surprisingly, it was proposed in the American Mathematical Monthly. Back in 2017. Well, the computations are a little bit more complicated than the Putnam one, and basically says that to show that, so prove that, the statement is the following: prove that the integral from 0 to 1 of x times natural log of 1 plus x, everything over 1 plus x squared dx is equal to, give me a second, I don't know it by heart. It's pi squared over 96 plus log 2 squared, so natural log of 2 squared over 8. Yes, that should be it. Okay. You see, this problem, the Putnam problem, is this is very related to that Putnam problem from 2005. The Putnam problem, remember, there was this no x here. This x was canceled. So that was the Putnam problem. So now we do have an x here. See, that was a Putnam problem without any x. Now we do have an x here. So, well, the thing is that, will this perturb me in any way? So let's proceed in the same way, an exact same way. So, so I'm going to insert a parameter, and I think it's better to do it inside the log. So consider f of a to be the integral from 0 to 1 of x times log of 1 plus x times a, everything over 1 plus x squared dx. Great. Clearly this integral converges. I have no problem. I don't think I need to go over this, explain this. Now let's take the derivative. So taking the derivative, we have, so we're going to have the following. So f prime of a, so this guy is nothing else than, okay, let's be careful here. So taking the derivative with respect to a, so it will be 1, okay, it will be x. So it will be the integral from 0 to 1 of x squared over 1 plus x squared times 1 plus xa dx. Great. Great. All right. So now we have to do the following trick. So I'm going to take out this 1 over a plus 1 squared times, I'm going to write this integral in the following way. So this will be ax minus 1 over 1 plus x squared plus 1 over 1 plus xa dx. Right. So so as you can see, I did this very tricky stuff. So now at this point, this will become pretty standard. So I'll just, this will be 1 over a plus 1, 1 over a squared plus 1. And now let's be careful here. So this would be, we can actually compute these integrals here. So it will be okay, so that would be the derivative. So it will be ln, okay, that will be ln of, so it will be a over 2 log of ln of 1 plus x squared minus arctangent of x plus log of 1 plus a, everything over a. Okay, great. And this goes from 0 to 1, which will give us so this would give us 1 over a squared plus 1 times a over 2 log of 2, ln of 2 minus pi over 4 plus, so this has nothing to, so this is a constant, log of 1 plus a over a. Okay, great. So that's what we get. Or if we just put everything together, if we do the computations, if we FOIL this, this would give us a over 2 log 2 over a squared plus 1 minus 5 over 4 over a squared plus 1, and the last one would be minus a log of 1 plus a, everything over a squared plus 1. Wow, look at that. Am I forgetting something here? So, okay. Plus now log of 1 plus a over a. Okay, I think that should be it. Anyway, it doesn't look nice. Let me just make it look nice. Okay. All right, great. Now it's pretty clear what we need to do. So now let I to this integral from to be the integral from 0 to 1 of to be our integral, in fact. Okay, so we have I, we denote I our integral. Then it follows that let's see, what do we have? Follows that I is f of 1, which is f of 0 plus, so using the fundamental theorem of calculus again, is f of 0 plus the integral from 0 to 1 of f prime dA. But we know who f prime is, so we're just gonna plug it in here, right? We computed f prime. Look, there's this monster here, all of it. So right, we're just gonna plug it in. So this will mean that let's be careful with the computations. Yes, f prime. So this would be f of 0. Wait, let me. Okay, so basically this would give us 0 plus 1/2. Let's be careful here. 1/2 log 2 ln of 2 times the integral of a over a squared plus 1 dA, right, minus pi over 4 the integral wait, from 0 to 1 is here. What's on from 0 to 1 of, or maybe see, 1 over a squared plus 1 dA minus minus the integral I, right? We have it there, here, plus the integral from 0 to 1 of, so you see this integral I, you have it here. So this guy here will give us the integral. So plus the integral from 0 to 1 of ln of 1 plus a over a dA. All right, I think it's pretty standard at this point. It's basically the only thing we need to take care of is the last integral, which I already solved. But anyway, I'll mention after at the end. So this would give us, let's see, so this is ln of, so this is 1/2 times log ln of 2 times log of a squared plus 1 over 2 from 0 to 1 minus 5 over 4. This integral is arctangent from of a me write it here, from 0 to 1, minus I, plus this last integral here. Let me write it, and then I'm going to say it at the very end. So this will give us, if we look, this would give us negative I plus six. Okay, so I'm just going to write it. So this would be negative I plus log 2. This would be log 2 squared. So ln of 2 squared over 4. And these two combined here will give us, so arc tangent pi squared over 6, pi squared over 12. So this would be, so plus pi squared over 48. Okay, I think. So this implies that I is finally pi squared to the 96 plus exactly what we wanted, log 2 squared over 8. And that's the final answer. All right, here I'm going to point out a remark which goes back to the Basel problem, basically. We use that the integral from 0 to 1 of ln of 1 plus a over a. This guy is pi squared over 12. And this goes back to the Basel problem at some point. Anyway, I discussed this, I think, in my one of my lectures. The Basel problem says that zeta of 2, which is this series, in fact, I will even discuss this problem when we is so the sum of 1 over n squared, so the sum of this series, right, is pi squared over 6. So this goes back to Euler back in the 1700s. Anyway, I will discuss a solution for this problem, for the Basel problem, when we as part of what you will see as a consequence of a differential equation. But anyway, we'll get to that point. All right, I think I'm going to stop here for the recitation. I will continue next time with more stuff about series of functions, and maybe how to take, well, maybe I'll do problems involving maybe even some dominated convergence theorem. In other words, I'm interested in how we're going to pass to the limit under the integral sign, or how we're going to commute the integral with the infinite sum and stuff like that. All right, guys. Thank you very much.